Hey there, it's Shannon Magic Myers, and today we're taking a look at a population of small animals where time is measured in months. So we've got this differential equation, dp dt is equal to k times p raised to the 1 plus c, where k is greater than 0 and c is greater than or equal to 0. So suppose for c equal to 0.01 that the nonlinear differential equation dp dt equal to k times p to the 1.01, that's just plugging in c to the equation given above and adding 1. K is greater than 0. It's a math model for a population of small animals where time t is measured in months. We're going to solve the differential equation subject to the condition that p at 0 is 10 and the fact that the animal population has doubled in 9 months. And we'll be rounding the coefficient of t to 6 decimal places. So let's do it. So we've got dp dt is equal to k times p to the 1.01. And one thing that's nice here is that it's separable, right? So if I divide both sides by p raised to the 1.01, on the left side we've got p to the negative 1.01 dp is equal to k dt. And then integrating both sides, well, when we add 1 to this exponent, we'll get p to the negative 0.01 divided by negative 0.01, just that power rule, is equal to k times t plus some constant. We'll call it c1. Groovy? All right, so now p to the negative 0.01 equals to negative 0.01 times kt, and then we're just going to be adding a different constant. So you don't have to write it as negative 0.01 times c1. We'll just write c2. And now I want to raise both sides to whatever number is going to give me a 1 for the p and the power. So negative 100 would be the winning choice. We'll get p to the 1, or just p. Actually, we'll write it as p at t is equal to quantity negative 0.01 k times t plus c2 raised to the negative 100. Cool so far? All right, so now we have to use the conditions that we've been given, these initial conditions. So we were given that p at 0 is equal to 10. So when we apply this, we'll put 10 in for p at t and 0 in for t. So we will get negative 0.01 k times 0 plus c2, and then all of that's raised to the negative 100. So that will be 10 equals to c2 raised to the negative 100, and then raising both sides to the negative 0.01 gets you a 1 exponent for the c2. And so 10 to the negative 0.01 is equal to c2. So now we will put that back in for p of t with the next little bit of information that we have. So p of t is equal to negative 0.01 times k times t plus 10 to the negative 0.01, all of that raised to the negative 100. Now we're going to use the doubling time so that we can find k. So using our next piece of info, we know that p at 9 equals double 10, which in other words is 20. And so using this in that new equation, we would set 20 equal to negative 0.01 times k times 9 plus 10 to the negative 0.01 to the negative 100. So this one's a little tricky. I'm going to keep that negative 0.01 with the k because we're going to be plugging that in again right over here. So I'll just keep them together instead of completely isolating k. So working through it, we will raise both sides to the negative 0.01 to get a coefficient of 1 around that quantity. So we'll have 20 to the negative 0.01 is equal to negative 0.01 times k times 9 plus 10 to the negative 0.01. And that will give us 20 to the negative 0.01 minus 10 to the negative 0.01 is equal to negative 0.01 times k, and then times 9. I'm going to go ahead and divide by 9. And so we get negative 0.01 times k is approximately equal to negative 0.000750. So again, bringing it back, adding the next piece to the puzzle, we have P at T is equal to negative 0.000750 times T. Just a reminder, in for negative 0.01 k, we're putting this amount here that we just found. And then plus 10 to the negative 0.01 raised to the negative 100. Cool? All right, so that is our model, and this finishes up the first part of the problem. So I'll go ahead and box this result, and then we'll go on to part B. So part B is asking us to take a look at what happens as P at T increases without bound. So what we found over here is called a Doomsday equation. So basically we have this P at T equal to negative 0.000750 times T plus 10 to the negative 0.01 raised to the negative 100. Now, if you think about it, if I rewrote this with a positive integer, P at T equal to 1 over negative 0.000750t plus 10 to the negative 0.01, all of that would be raised to the positive 100. Now, do you see what would happen is we got very, very close to 0 in this quantity here. Do a different color. In this quantity inside that's being raised to the 100, then that would send P at t to infinity. So what we're going to do is we're going to substitute in capital T for t, and we're going to basically just say, all right, well, I'm going to let 0 equal to, or I'm going to set what's inside there equal to 0. And call it capital T because we're doing something different with it. And I'm just going to look at that quantity, because as that quantity gets super close to 0, the whole thing is going to go to infinity, right? So, and it'll be positive because you're raising it to the 100th power, which will make it positive. So now, isolating t, we would get 10 to the negative 0.01 over positive 0.000750, which is approximately and that is in months. All right, so then the last part is just asking us to find P at 90 and P at 180. So we'll go ahead and do so. So remember, our P at t is equal to negative 0.000750 times t plus 10 to the negative 0.01, all raised to the negative 100. And P at 90 will be, we're going to be rounding it. Well, actually, it's already rounded. So we'll get, so that one's approximate, negative 0.000750 times 90 plus 10 to the negative 0.01, all of that raised to the negative 100. So entering that into the calculator, so from my calculations, it might be a little bit of a rounding error, but I got 12,839, and that would be animals. We don't know what kind of animals they are. This result's a little bit off from the answer in the back, but it's probably just a little bit of a rounding error. And then if we go to P at 180, that's going to be approximately, you just plug in 180 instead of 90. So I'm just going to hit second entry. And then this one is animals. Cool, cool. All right, there you go. I hope you're having a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please hit that subscribe button and the like for the video. And talk to you soon. Bye.